Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be continuing our lecture on acid-base chemistry. And our first topic today is going to be over weak acids and bases. Weak acids and bases are substances that only partially dissociate in aqueous solutions. Unlike strong acids and bases, which completely ionize in water, weak acids and bases reach an equilibrium state where both the ionized and unionized forms coexist in solution. Let's start with discussing weak acids first. A weak acid partially dissociates in water to produce hydrogen ions and its conjugate base. And the degree of dissociation is quantified by the acid dissociation constant Ka. Here you see the general dissociation reaction for a weak acid. Our weak acid reacts with water to produce hydronium ions and its conjugate base. And we can go ahead and write the equilibrium expression for this dissociation as the concentration of the products raised to their respective stoichiometric coefficients divided by the reactants raised to their respective stoichiometric coefficients, and we do not include liquids or solids in these equilibrium expressions. So for Ka, we have the concentration of the hydronium ions multiplied by the concentration of the conjugate base, and this is all divided by the concentration of our weak acid. Now, the smaller the Ka, the weaker the acid, and the less it will dissociate. What about weak bases? A weak base partially dissociates in water to produce hydroxide ions and its conjugate acid. And here again, the degree of dissociation is quantified by the base dissociation constant, Kb. Here we see the general dissociation reaction for a weak base. Our weak base in water reacts to form hydroxide ions and our conjugate acid. Now we can go ahead and write our equilibrium expression for this dissociation. Kb is equal to the concentration of hydroxide ions multiplied by the concentration of the conjugate acid. And this is all divided by the concentration of the weak acid. The smaller the Kb, the weaker the base, and the less it will dissociate. Now that we have a solid understanding of weak acids and bases, including their partial dissociation and the equilibrium constants, Ka and Kb, we can naturally transition into the concept of conjugate acid-base pairs. This concept is closely linked to the behavior of weak acids and bases in aqueous solutions. When an acid donates a proton, it forms its conjugate base. On the other hand, when a base accepts a proton, it forms its conjugate acid. This proton transfer process highlights the dynamic equilibrium between acids and bases. Conjugate acid-base pair consists of two species that transform into each other by the gain or loss of a proton. Now, in regards to conjugate acid-base pairs, there's a couple of general principles to keep in mind. The first principle deals with the formation of conjugate pairs. Every acid has a conjugate base that's formed by the loss of a proton, and every base has a conjugate acid formed by the gain of a proton. The second principle deals with strength. The strength of an acid is inversely related to the strength of its conjugate base. So a strong acid has a weak conjugate base, and a strong base has a weak conjugate acid. The final principle deals with equilibrium. In an equilibrium mixture, the position of the equilibrium can be influenced by the relative strengths of the acids and bases involved. Now, there's also an important concept that we need to discuss here. When you have a weak acid dissociating in water, and its conjugate base acting as a base in water. The combined reactions essentially represent the autoionization of water, and the same is true for a weak base and its conjugate acid. Allow me to demonstrate. So here what we see are two reactions that deal with bicarbonate and carbonate. So these are two reactions related to the acid-base behavior of bicarbonate and carbonate. In this first reaction, we see the acidic behavior of bicarbonate. Bicarbonate acts as an acid, donating a proton to water, forming hydronium ions and producing carbonate as the conjugate base. And we can go ahead and write the equilibrium constant expression for this dissociation by writing that Ka is equal to the concentration of the products raised to their respective stoichiometric coefficients divided by the concentration of the reactants raised to their respective coefficients. And we notice that water is not included because it's a liquid. Now, carbonate, we see it in this second reaction. This shows the basic behavior of carbonate. Here, carbonate accepts a proton from water, producing bicarbonate and hydroxide ions. And this reaction reflects the tendency of carbonate to act as a base in aqueous solutions, and we can go ahead and write the equilibrium constant for this process, Kb, same format. It is the concentration of the products raised to their respective stoichiometric coefficients divided by the concentration of the reactants raised to their respective stoichiometric coefficients, not including liquids or solids. Now, when you add these two reversible reactions together, you essentially describe the autoionization of water, where water molecules react with each other to form hydronium ions and hydroxide ions. Since this net reaction represents the autoionization of water, the equilibrium constant for the combined reaction is the product of the individual equilibrium constants, and this is equal to the water dissociation constant Kw, which is equal to 10 to the minus 14 at 25 degrees Celsius. And for any conjugate acid-base pair, this relationship holds true, and it demonstrates that the strengths of the conjugate acids and bases are inversely related. If one is strong, then the other must be weak. Let's go ahead and move into a practice problem now. This problem says the pH of a 0.05 molar solution of a particular monoprotic acid was measured and found to be 3.50. What is the Ka for this acid? Now, for this kind of equilibrium-based problem, we can usually follow two steps to ensure we get the correct answer. The first step is to set up the ice table. And then the second step is to insert the equilibrium values from the ice table into the equilibrium constant equation. So for our reaction here, we have our monoprotic acid in water. It's going to form hydronium ions and its conjugate base. We're going to go ahead and do that first step. We're going to set up an ice table for this reaction. I stands for initial concentration, C for change in concentration, E for our equilibrium concentrations. Now, starting off, we have 0.05 molar of our monoprotic acid. Now, this acid hasn't dissociated in solution yet. That means our concentration for our hydronium ion and our conjugate base is 0. Now, over time, our monoprotic acid is going to dissociate into solution. So we're going to lose some of that monoprotic acid as it dissociates to form hydronium ions and our conjugate base. And we're going to use X as the variable to denote that change. With that, we can go ahead and write our equilibrium concentration. This is going to be initial plus or minus our change. So for our monoprotic acid, this is going to be 0.05 minus X. And for our hydronium ion concentration, it'll be just X. And the same for our conjugate base concentration, just X. Now that we have our ICE table set up, let's go ahead and write our equilibrium constant expression. This is going to be the concentration of our hydronium ions multiplied by the concentration of our conjugate base divided by the concentration of our weak acid. And we can go ahead and replace our equilibrium concentrations into this expression. So this is going to be X multiplied by X divided by 0.050 minus X. Now, our goal here is to figure out Ka for this acid. And in order to figure out Ka, we need to know what X is. We're not given that directly, but the key point to recognize about this problem is that anytime we know pH, we can quickly determine the equilibrium concentration of hydronium ions. We're given the pH of this solution, 3.50, and we can figure out the concentration of hydronium ions because that is equal to 10 to the minus pH. So that's going to be 10 to the minus 3.50, which is equal to 3.16 times 10 to the minus 4 molar. Now again, we said that this is the concentration, our equilibrium concentration of hydronium ions, which means it tells us what X is. And that's really important because now we know what X is, we can take this value and plug it back into our Ka expression and calculate the Ka. So now our equation looks like this. Ka is equal to 3.16 times 10 to the minus 4 multiplied by 3.16 times 10 to the minus 4. And that's all divided by 0.050 minus 3.16 times 10 to the negative 4. And if we plug this into our calculator, we're going to get that our Ka is equal to 2.0 times 10 to the minus 6. And we got our final answer. Beautiful. Let's do another one for good measure. This problem says determine the pH of 0.075 molar pyridine. The Kb value for pyridine is 1.7 times 10 to the minus 9. Now, if you're asked about a substance that you're not familiar with, you may wonder whether this substance is an acid or a base. The tip-off for this substance is that it has a Kb value, making it a base. And all weak bases behave the same in water. So we're going to go ahead and write the general dissociation reaction of a weak base in water. It results in the formation of hydroxide ions and a conjugate acid. So we're going to go ahead and write that down. Now from here, we can solve this problem by following our 2 steps for equilibrium-based questions. First step, set up the ICE table. Second step, plug the values from the equilibrium line of the ICE table into the equilibrium constant expression. Here for the ICE table, for that first step, I stands for initial concentration, C stands for change in concentration, and E stands for our equilibrium concentration. We start off with 0.075 molar pyridine. That is our weak base. Initially, it hasn't dissociated yet, so our concentration for our hydroxide ions and for our conjugate acid are 0. Then, over time, the weak base reacts in solution, and we form our hydroxide ions and our conjugate acid. So we're going to be losing some of our concentration for our weak base, and instead we'll be forming hydroxide ions and our conjugate acid. So we're going to denote X as our variable of change. Then our equilibrium concentrations are just going to be initial concentration plus or minus change. For our weak base, that's going to be 0.075 minus X, For hydroxide ions, just X, and for our conjugate acid, also just X. Now, our second step is to plug the values from the equilibrium line of the ice table into the equilibrium constant expression. So here, Kb is going to equal the concentration of hydroxide ions multiplied by the concentration of our conjugate acid divided by the concentration of our weak base. And we can go ahead and again plug the values from the equilibrium line into this equation. That's going to be X multiplied by X over 0.075 minus X. Now here we're going to make an approximation. We're going to use our 5% approximation rule. We're going to say since Kb for this base is very small, we can assume that 0.075 minus X is approximately equal to just 0.075. And that way, we can rewrite Kb to equal X squared over 0.075. Now here, we want to plug in what we know for Kb and go ahead and rearrange this equation to solve for X. We're given Kb in the equation, so this X squared over 0.075 is equal to 1.7 times 10 to the minus 9. Then we can rearrange this equation to solve for X. X is going to be equal to the square root of 1.7 times 10 to the minus 9 multiplied by 0.075. And this is going to give us that X is equal to 1.13 times 10 to the minus 5. Now, since we used our 5% approximation rule, we want to triple check that we did that appropriately. And the way we do that is we take our value of X, divide it by our initial concentration, and multiply that by 100%. So this is going to be 1.13 times 10 to the minus 5 divided by 0.075 multiplied by 100%. This is going to give us 0.015%. This is much smaller than 5%, so the approximation was appropriate. Now, this is our value for our hydroxide ion concentration. If X is equal to 1.13 times 10 to the minus 5, and we expressed that the equilibrium concentration for our hydroxide ions is equal to X, we now have enough information to calculate the pOH. Now, I know that's not what this problem asked for, but that's the first step we need to do. Because we're dealing with a weak base, we have our hydroxide ion concentration. We can use that to calculate pOH, and then from there we can finally calculate the pH. Now remember, pOH, that's equal to the negative logarithm of our hydroxide ion concentration, which we know is equal to X, and X is equal to 1.13 times 10 to the negative 5. And if we plug this into a calculator, we're going to get that the pOH is 4.95. And because we now know the pOH, and we know that pH plus pOH is equal to 14, we can isolate the pH variable to solve this problem. pH is going to equal to 14 minus pOH, so that's 14 minus 4.95. The pH is equal to 9.05. And there we have it. We solved this problem. Now let's move on to our third objective, which deals with polyprotic acids. Polyprotic acids are acids that have more than one ionizable proton, meaning they can donate more than one hydrogen ion. Some common examples include sulfuric acid, phosphoric acid, and carbonic acid. And actually, in this chapter, we're specifically going to talk about diprotic acids and triprotic acids. Diprotic acids, these acids have two ionizable protons, so they can undergo two ionization steps, each with its own dissociation constant, a Ka1 value and a Ka2 value. Triprotic acids, these acids have 3 ionizable protons, and so they undergo 3 ionization steps, and each step has its own dissociation constant, Ka1, Ka2, and Ka3. Now, let's focus on diprotic acids because they provide a simple example that helps us understand how polyprotic acids behave in solution. So let's take a look at sulfurous acid as an example. Sulfurous acid has 2 ionizable protons, and it ionizes them in 2 distinct steps. So in our first step, the first ionization of sulfurous acid occurs when it loses its first proton, forming hydrogen sulfite ion. The strength of this ionization is described by the dissociation constant Ka1, and that is equal to 1.7 times 10 to the minus 2 for this particular reaction. Then we have our step 2. So after that first proton is removed, the hydrogen sulfite ion, it can lose a second proton, forming the sulfite ion. Here, this second ionization, first thing to notice is it's much weaker, and the dissociation constant for this step is Ka2, which is equal to 6 times 10 to the minus 8. So as you can see here, it's a smaller value for Ka2, meaning it's much harder for sulfurous acid to lose the second proton. Now, an important pattern with polyprotic acids is that the first ionization step is almost always stronger than the subsequent one. And that is reflected in the dissociation constants. For sulfurous acid, for example, we clearly saw that Ka1 is greater than Ka2. This tells us that the first proton is easier to remove. The first proton comes off much more easily than the second. This trend is something you'll see with most polyprotic acids. Each successive proton is harder to lose, and the dissociation constants decrease accordingly. So to sum up, polyprotic acids can donate more than one proton, but each proton is lost in a separate step, and each step has its own dissociation constant. With that, we can move on to the fourth objective, which we'll actually cover in the next video. So that's it for now. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.